Easy question. No, you don't have to. It always is.
So all of you have been in circuit 1 at some point, right, in the past. Did you do that, Ryan? Okay, great. So there are 2 problems for this lab. The first one, you need to use superposition to solve this problem, and SPICE code only. You are not supposed to use symbols to build a circuit in LT-SPICE. If you have forgot it, you can check out these videos, superposition, Thevenin's, and how to use LT-SPICE code. I think this one is compared to this one, this is pretty simple. If you have any questions, you can ask me. I will be around during the lab to help you out. And for the second one, we treat this capacitor as a load, right? So the load means when you are doing a Thevenin's equivalent circuit, you want to remove the load and look back to find out RTH, right? And for ETH, you also want to remove the load and find out the voltage here. So it's going to be the ETH. For time delay, here's an important concept. If you were in my circuit 1, you probably have learned it for a few times. No, it's fine. It's pretty simple. We don't need to derive the equation. You guys just need to know if you have a circuit like this. That's V in. Here's V out. Right? And that's a resistor, that's a capacitor. So that's the RC circuit model, the simplest model for the RC circuit analysis. And you can imagine that a capacitor is actually a water bucket, and this is a pipe or water source. You are trying to dump water into the bucket. It takes time, right? So that's why you get a time delay whenever you are charging up the cap. But instead, it's actually dumping charges, electrical charges, into the capacitor. It's the same as you are dumping water into the bucket. So the resistor here is limiting the current, and it's not like you have a infinite amount of current to dump into the capacitor. This is limiting the current. So whenever you have a larger R, you get a less current, so it takes longer time to charge up this capacitor. And if I draw the input and output signal diagram, for example, here is a digital signal, or pulses, digital signal, just pulses, as V in, that's V in. V out looks like this. Right? Because there will be a time delay. So time delay is measured as you just use a cursor in LT-SPICE and point to 50% of the Y value. For example, this is 5 volts. And you find out here's 2.5 volts. And then whenever it is at 2.5 volts, the corresponding X value to the original time point. So this time difference will be the time delay. And this value equals to 0.7 RC. This was derived in one of the lectures in my Circuit 1 class. And if you go to the YouTube channel playlist I sent to you guys by email yesterday, and I have shorter videos over there. That's for the online course instead of the 55 minutes courses in the past. That takes really long time because I have interaction with students. It takes 55 minutes. But for the YouTube playlist, I have really brief videos to cover all these concepts. You can find out how I derive it over there. But you don't need to know that for digital class, for this class. You just need to know the TD will be 0.7 RC, and the TD is a function of R and C, and there's nothing to do with voltage. If I'm using a 5 volts input, you are going to see a signal diagram like this. If this is 2.5 volts, right, it's not shooting to 5 volts, it's just stop at 2.5 volts. It's going to be the same time delay because time delay is 0.7 RC, but nothing to do with the voltage, right? Okay. That's one thing you need to know. And if you have a larger R, you are going to have a larger time delay because the larger R is going to limit the current. You have less current to be dumped into the capacitor. If you have a bigger bucket, it takes longer time to charge it up to the full range, right? So bigger R, bigger C will give you a bigger time delay. And RC, we know 0.7 RC is the time delay, but there's another concept. It's called tau, right? Tau equals to RC. It's called time constant. Is to let you to do a really quick calculation to find out the time constant of the circuit, so you'll know what's the range of the time delay is for the system. You know, it doesn't have to be a really accurate value. For example, for this circuit, if I have 1K, 1 nanofarad, what's the time constant? 1K times 1 nanofarad will be 1 microsecond. So that's interesting because R is ohms, C is farads, and R times C is second. Is time. Okay, so that's the time constant. So you know R times C is going to be 1 microsecond. So you know the circuit system for this circuit, the time delay is in the range of microseconds, right? Not nanoseconds. Why is this important? So because when you are trying to create a pulse function for this circuit, you know this circuit only works for something longer than a few microseconds. You know what I mean? Because time delay is already in the microseconds range. If you have a nanoseconds pulse, it's like, okay, let me draw it. So for example, this is the same coordinate, and here, this is not even nano. This is probably hundreds of nanoseconds period, like this. That's a totally different frequency, right? Can this signal drive this circuit? So I'm saying drive, right? Drive means it is able to fully charge and discharge the cap without distorting the signal. So if you have something like this, what the output looks like? You know, the time delay is already 1 microsecond, or actually 0.7 microseconds. And you have such a short period and such a short on time. Keep in mind, only the on time is charging up the cap, but off time is discharging the cap, right? So what's going to happen is it's not able to fully charge the cap, and then it's going to start discharging it. So it's going to start oscillate. It's not stable. So what's going to happen is you have this, and the output will look like like this. Because if we align this one to here, from this signal to here, this time, this little T on here, on time, can only charge the capacitor to this voltage. So that's why it's going to stop here and then start discharging. It's going to start oscillating like this. That's not correct. I didn't provide you a pulse function, but you have to define the pulse function by yourself. So if you look at the website, the pulse function, and after convert everything to the Thevenin's equivalent, you are going to have RTH and VTH. If the pulse function over here for this original circuit, you defined something like let me write it down because For the original circuit, for example, defined pulse to be, so what's the first argument? The V low, right? V low is 0, V high is 5, time delay is 0, and rising time, it just make it really sharp. This pretty close to no time delay for the original signal, so you can measure the time delay. You can imagine if you have an input signal like this, and your output will be like this, it's bad. So you need a sharp, really steep rising edge for the input signal. So just 1 picosecond. It cannot be 0 because nothing cannot be 0. It takes time from 0 to jump from 0 to this, right? It's not a god. It's something in real life. So just make it really short, 1 picosecond, for example, for rising edge, and falling edge, 1 picosecond. And what's next? T on, right? T on. Let's say. So how can I define T on? So here's the question. If you understand this, let's look at the original circuit. Let's just look at this one. It's pretty similar, just different RNCs. So for this RNC, what's the time constant? What's the time constant? 1 micro, because 1K times 1 nano is 1 micro. 1 times 10 to the negative 6, right? So you know the time constant is in a 1 microsecond range, right? You can imagine if your T on is shorter than the time delay, you cannot fully charge your capacitor to the full range. So your T on has to be longer than the time delay or the time constant. I know 0.7 RC, but RC similar, right? Close to 0.7 RC. Just do a really quick approximation. So you know RC is 1 microsecond, so T on has to be longer than that, so you cannot have your T on to be 1 nanosecond. So what about like 5 times longer than this? Right? It makes sense. So you can have this types of diagram in your simulation. 5, 10 doesn't matter. You don't want to just make 100, then you have to zoom in a lot trying to see the edge and the time delay. It's not convenient. Let's just make 10 times longer, for example. So 10 microseconds for the T on. For T on means, so this time period is T on, this T off, right? So T on here, let's define it as 10 times longer than this, so we can have a really nice diagram. So T on should be 10 microseconds, just 10 micro, 10 U. And T off, no, the period. So T on and period. Because this is T on, this is period. However, you have a little 1 picoseconds rising edge, so the rising edge, falling edge takes 1 picoseconds for each. It's minimal, but we have to. If you just set up here is 10 micro and this is 20 micro, LT-Spice cannot understand it because you have 2 picoseconds at the edges. Let's just make it a little bit longer, like 20.1. What about that? That works. Definitely can cover that 1 picosecond. Or 21, doesn't matter. Just make the pulse that looks like 50% duty cycle. So 20.1 microseconds for the period. No, let's just do 21, doesn't matter. So here's the pulse function. You can use as your circuit. And in your SPICE code, what you can do is just replace the original DC voltage with this pulse function. You know what I mean? We have this here, right? So this is V in from 0 to 1, and this is from 2 to 0. And when you are writing your SPICE code, you have V in is from 1 to 0, which is pulse. Instead of DC voltage, you just put a pulse here. Right? And then just follow all the same SPICE code for the DC circuit. So another thing you need to know, which is the original circuit, you have 2 different circuits. The original one and the Savigny's equivalent circuit. So the original one, if you set up a 5 volts for the pulse, and you have so many resistors here, you can imagine that the voltage here, the pulse, cannot shoot to 5. It's being divided, attenuated, right? So if you just have this circuit in LT spice, and if your input is 5 volts, if that's your input, you can predict that the output will be something like this, right? Because the DC voltage is being attenuated. It's a voltage divider. So how do you find out the time delay in here? It doesn't matter if it's shooting to 5 volts or shooting to the ETH. Doesn't matter. It just point to 50% of the output signal. 50% of the output signal. And look at the X value, which is the time, right? Here's the time of the 50% of the output. And just measure the time difference between these two. Because it doesn't matter if it's 5 volts or ETH, it's just one edge. And we are giving a really sharp edge. So we consider that there's no time delay at the edge. So we just point the first cursor right at here, at the very beginning or in the middle, doesn't matter because it's only 1 picosecond here on the edge. Right? You point to the very beginning of the edge or on the top or in the middle, doesn't matter. It's just one picosecond difference as a maximum. So just to point the first cursor here and the second cursor here and measure the difference, and you can get the time delay. It doesn't matter if one looks higher than the other one. It won't be always like this, but it doesn't matter at all because the input has no time delay ideally. And you directly put 1 picosecond there, it's just, you can ignore it. So you can measure your time delay, use this circuit, you can build it in LT Spice and you can do it like this, or you can convert whatever here, the voltage source and the resistor network, whatever in here in the black box, convert it into the equivalent circuit, which will be a 7-inch voltage and 7-inch resistor. And then you run this again, and you will see a diagram like this instead of this, because there's no attenuation. It's just one resistor, one voltage, right? Let's see if I'm missing anything. Any questions or anything? Yeah, I think that's it. Okay.